Hello, I'm Laura Mazzola, and you're watching the video abstract of sudden transition between classical and quantum decoherence. This work has been done by myself, your Piilo and Sabrina Maniscalco, here at the Turku Center for Quantum Physics. You can find our paper on the arXiv at this address. In this paper, we study the dynamics of classical and quantum correlations in a system of two non-interacting qubits under local non-dissipative channels. To quantify quantum correlation, we use the concept of quantum discord, which is defined as the mismatch between the quantum generalization of two classically equivalent expressions of the mutual information. The main result of our work is that we demonstrate the existence of a class of initial states for which the quantum discord is completely unaffected by decoherence for a long interval of time. To be more specific, we distinguish two dynamical regimes. Initially, the classical correlation is lost, while the quantum discord, so quantum correlation, remains constant, completely unaffected by the interaction with the environment. And this is what we call a classical decoherence regime. Then, at a specific interval of time, t bar, which depends on the initial state of the system and on the specific parameter characterizing the dynamics. After this, at this particular instant of time, the system goes to a different dynamical regime in which quantum correlation starts to decay, while classical correlation becomes constant. And this is what we call the quantum decoherence regime. So in this sense, we talk about a transition which is sudden because it happens at a specific point of time between classical and quantum decoherence. To better understand our results, we looked at the time evolution of entanglement and other than entanglement quantum correlation in our system, while the discord is constant. And in particular, we use the new definition of discord and of correlations in general in a quantum system, defined by Modi and co-workers. Their key idea is to use relative entropy as a distance measure of correlations. So in their approach, the discord is the distance of the state under investigation to its closest classical state. Entanglement is the relative entropy of entanglement, and they introduce a new concept, which is the dissonance, a new quantity, and the dissonance quantifies other than entanglement correlations, and it represents how non-classical the closest separable state is. So we looked at the time evolution of entanglement and dissonance while the quantum discord is constant, and we found out that entanglement is decreasing as we expected, but other than entanglement correlation, so dissonance, is actually increasing. And this is quite a surprising result because it means that other than entanglement correlation is increasing under decoherence. So we believe that our results are quite counterintuitive, and they open a series of new interesting questions, as for example, which is the most general class of initial states or of open quantum systems exhibiting a sudden transition from between classical and quantum decoherence, or time invariant under decoherence discord, or is it possible to use those phenomena in some quantum computation task? And most importantly, what are the physical mechanisms behind what we found out? So, well, we don't have yet the answers to these questions, but the search continues. So thank you for your attention.